let's continue with our discussion of computation and what it is. So, what do programs compute? Let's consider a couple of examples. We started answering that question in the previous screencast, so let's look at two concrete examples of L programs. So both of which we actually analyzed in the previous screencasts on the theory of computation. So let's this is program P2, and to the left is program P1. And the question that we would like to answer, the two questions we would like to answer in this screencast are what does P1 compute and what does P2 compute? So formally, what is psi P1 of x, and what is psi sub P2 of 2, because P2 has two arguments and P1 has one argument, only x1 in the text of the code. And what is psi sub P2 of 2? Right, and remember, this is the what is psi P1 of 1? This is the value of x in the terminal snapshot. And so if you look at it, x1 is decreased until it gets 0, and y is increased by 1 until x1 is 0. So psi P1 of 1 of x1 is equal to x1, because the value of y in the terminal snapshot is the value of x1. Or, more generally, psi sub P1 of 1 of x is equal x. Now let's go take a look at P2. We've also taken a look at it before. So y is assigned x1, z2 is assigned the value of x2, and then we decrement z1 by 1 and increment y by 1. So y gets to have the value of x1 plus x2 when the computation is over, when we go to E1, the end label. So psi of P2 and 2 of x1 and x2 is equal to x1 plus x2. Another important question, both practically and theoretically, is what to do with superfluous or insufficient inputs. So let's say that we get more arguments than necessary, or fewer arguments than necessary. So let P have n inputs, and they all can be characterized as, let's say, x1, x2, and all the way up to xn. And what is the value of psi pi of m, of r1, rm, if m is not equal to n? So there are two cases. M is strictly less than n, so we get insufficient inputs. And the second case is m is strictly greater than n. We get superfluous inputs. Okay, so let's consider the first case of insufficient inputs. So specifically, we have some program P, and it has x1, x2, xn, n input variables. right, xm, and then n xn. And we place the inputs into the first m variables. R1 goes into x1, R2 goes into x2, and then Rm goes into xm. Now, the remainder of variables default to 0 in this case. So in case of insufficient inputs, all of those variables that are not given the value default to 0. And in the second case, we get superfluous inputs. So in that case, we have, okay, let me erase this. In that case, we have x1, x2, and okay, well, x3, xn, and we get so these are the inputs, and then we get the values, right? R1, the input values that we actually give the program, R2, and then R3, Rn, and but there are more values than inputs, or input registers, if you will. So all of those extra or superfluous inputs are ignored. So we can have program, if the program has 5 inputs and we give it 6 or 10, all of those extra inputs will simply be ignored by the program. So a couple of concrete examples. Let's say that we have a program P of 2 arguments, x1 and x2, and that program will compute the product of x1 and x2. And well, we'll consider, so let's say in the first case, let's consider what happens if we give it 1 argument. In the first case, the second argument defaults to 0 because we have insufficient input, and well, we'll just default the input that we have not been given to 0, so it's going to be 0. If we get 2 arguments, then the computation proceeds as specified, right? We just compute the product of 2 values. And in the third case, let's consider third case in which we give the program 3 inputs, x1, x2, and x3. In this case, we'll still compute x1 times x2 because the superfluous input, x3, will simply be ignored. So it's still x1 times x2, and x3 is ignored.